don't care. Yeah, the lanyard's green now. I can believe that. All right, so let's handle this a bit. When I was working this with students last night, one of the things that came to mind was that when we're talking about this kind of problem, I don't want to build it up anymore in your mind. There's several. You can't. That doesn't work. It's got to be both grays off and the red on. Sorry. It works for me, but I don't know if it works for you guys. I don't care. So I was talking. I don't even know where I was. So anyways, we're working at there's a lot of pieces in this puzzle, and you have to do all of them just right to get to that final thing. Now, on an AP exam, they're going to break this up into smaller pieces. They're going to ask you a piece of this at a time. They're not going to just jump into, do you have to push on the dielectric, or will it be pulled out of your hand? That will not be the only question they're going to ask. There'll be a variety of questions leading up to that. So I want you to understand, ultimately, it's about work. And at the end of this, we'll take a few minutes and talk about what's really going on microscopically, because I think that makes a big difference. And I think our discussion yesterday, trying to talk about what's happening with the individual charges, I hoped helped you and solidified in your mind some of the ideas about why the charges were doing what it is they were doing. So let's take a look at this particular example. And I want to put some numbers to it, not because I think numbers make it easier, but because in this circumstance, I don't think letters are going to really drive home what's happening. So I want to start with a relatively straightforward, and I'm going to use actually, I need to draw this. I can't use shapes. I'm going to start with a relatively easy circuit, I guess. I wanted to choose one last night that I knew would reduce easy. I'd like to do that again today. So we'll do 2 in series. And I want to try and use some numbers here that I think will work out easily, maybe. Yesterday we did 30 volts, and for this one we did 3 microfarads and 6 microfarads, and it worked out pretty well for this example. Now we're going to have a dielectric that's Mr. Shelton, be better. A dielectric over here with the value of, I don't know, give me an integer.
3 is 16.
We'll go with 3. One of the questions that was asked was, where should we place the dielectric to maximize the amount of energy stored in this circuit? And I think there are a couple of things I would encourage you to think about when it comes to this circuit. I'm trying to do something deliberate here too, by the way. I'm trying to talk a little bit more slowly. I think sometimes the nuance gets lost because I start getting wrapped up and start speaking faster and faster, and it doesn't give you time perhaps to process. But it's hard for me to slow down. So, if it sounds halting, it's because it is hard for me. When you're asked a question like that, you don't have to calculate the answer. You can think it through, I believe. So let's talk a little bit about capacitors in series. Their total capacitance will be less than the smallest capacitor in series. That's just an artifact of adding the inverses and inverting. So without even calculating it, I know that the total capacitance is less than 3. If I want to maximize the energy stored, I want to maximize the capacitance of the system. If I make the 6 microfarad capacitor bigger, I don't arguably have a chance to really change the capacitance very much, since I know that the total capacitance is still going to be less than 3. What I'd really like to do is find the smallest capacitor here and increase its size, because that allows us to elevate the capacitance at a much greater degree for capacitors in series. This is less true for ones in parallel because just add them together. So maximizing the capacitance there will be about finding whatever the biggest one is and tripling it. But I think in this case, if I want to maximize the capacitance, I want to increase whatever the smallest capacitor is in series so that I elevate the total capacitance as much as possible. So I don't want you to have to do all of the work to figure that out. If you went in that problem and went all the way to compare the two amounts of energy stored, you went way too far, because you should have stopped the moment you realized that the energy stored is equal to 1/2 CV squared. And the voltage wasn't going to change. You were focused, I hope, on the equivalent capacitance. Which case had the greatest equivalent capacitance? And that should have told you without doing any work. If you went the other way and had to work them out, you lost too much time on the AP exam. They are hoping that you will waste that kind of time. And you really need not to. So here's what I'd like you to do. I would like you to find the energy stored in the circuit before I put the dielectric in the circuit. That's going to take you a moment or two, so I will give you a moment or two. And you should all be able to do this without incident. So I have confidence I can pick on one of you. And you know what I'm going to do, because I want to make the numbers work a little bit better? Let's just go ahead and say that these are farads, not microfarads. That's terribly unlikely, but it will make your work easier. So you've got like 120 seconds, and then I will pick on one of you. So 900 joules of stored energy. It's important to note that the equivalent resistance was 2, because we're going to need that later. So I'm going to just kind of draw a small circuit down here. And remind myself that this was 2 farads. Now, when we put the dielectric in, we change one of the capacitors to 9 farads. This is because the dielectric merely multiplies the total capacitance, changes the permittivity of the air space, between the vacuum between the gap. So we need to figure out what the new equivalent capacitance is before we go any further, which is just going to be 1/9 plus 1/6. And take the inverse of this. And what do you guys get for the capacitance here? Say again?
18/5.
There it is, 18/5 farads. So this is 3.6, a clear increase in the equivalent capacitance. So it's going to have a clear impact on how much energy is stored, because the capacitance went up, the voltage remained the same. So now it's 1/2 times 3.6 times 30 squared, giving you, what was it, like 1620? So this one stored 900 joules. This one stored 1620 joules. That energy has to come from somewhere. Now, that means that if you're trying to put the dielectric between the plates of the capacitor, you're going to have to apply an external force to do work in applying that dielectric to the capacitor. Now, just keep an open mind here. If I tell you this is 20 centimeters, you should be able to tell me how much work, right? More importantly, you should tell me how much force. So I tell you it's 20 centimeters across, and we assume a constant force. You should be able to set that work equal to force times distance and tell me with what force it would be required to get that dielectric in there. All of those things are perfectly acceptable problems. But there's not a whole lot of meat there. Are there any questions about doing this portion of the problem? Because the next part of the problem is obviously charging up the system of capacitors and disconnecting it from the applied voltage. This changes the nature of the problem dramatically. The problem works in this way because while connected to the potential difference, the one thing we never talked about here is what's happening to the charged particles. And that's making a difference. The reason why when you go to try and push this dielectric in between the plates, while there's a potential difference there, there is an electric field there. And that electric field is applying a force to the charges in the dielectric. And it's opposing their motion into the field because there are charges there. Now, when you start putting that dielectric in the field, you are also at the same time changing the field. You're making it larger. This is pulling charges out of the battery in order to respond to the fact that your capacitor is increasing its capacitance and can hold more charges. But the force, the reason why you have to push, it comes right back down to F equals Q times E. The electric field that's already established there is applying a force to the charged particles in the dielectric. You are having to overcome that force. So the next part of this problem is to compare what happens when the system is charged already, but then disconnected from our voltage source. So we begin with a charged system and then disconnect it and attempt to put the dielectric in between the plates. This problem isn't the same. It's, I'd say, harder. It's not much harder, but it is harder. So how many of you feel like you can take this one on too? A little more tentative there. So let's talk about what you're going to need to do. First, this doesn't change. This 900 joules, that doesn't change. So we already have a baseline for how much energy is stored there. What does, on the other hand, change is when you go to put the dielectric between the plates of this capacitor, the equivalent capacitance is still going to be 3.6. But you have to be aware that the voltage no longer has to stay the same. The charges are going to move around. Or they're going to try to, I guess. But there's no place for them to go. I mean, we've got charges on the top of this. Let me get that off of there. We got charges that were on the top of this capacitor. Say a bunch of positive charges here. When we go to put the dielectric in there, they want to change the electric field. They're going to push on those charged particles. But I can't draw any more charged particles from the battery. Therefore, I can't push these particles anywhere. They're not going to leave. There's no place for them to go. And even though there's this part here in the middle, and we can say this capacitor, it's not changing. So could it accept more charges, or could I pull more charges from it? You can't. Because whatever amount of charge is on this plate that's positive has to have an equal amount of charge on this place that's negative. That can't change. So in this example, we are going to be manipulating the voltage because we're changing the electric field, but not changing the charges. So although there's 900 joules here, when you go to insert this dielectric into the top capacitor, you're really only changing that capacitor. But when you do, you're going to be changing the voltage of the system, which is going to change the energy across both capacitors. So what you have to do first and foremost is figure out how the voltages change across both capacitors due to the insertion of this new dielectric. I'll give you a few minutes to bat that around. Let's go with like 2 or 3. You either can get a start on this or you can't. Give it a few seconds and see what you can do. Let's see who knows what to do here and who doesn't. So I could call on Max or Shreyas because they did this problem yesterday. I think it was almost exactly the same, wasn't it? We didn't do putting it in here with it disconnected? Oh, well, good. I thought we did, but I was also doing some mechanics work with other folks and trying to answer Ivan's question all at the same time. So let's see, Matt, what do you think we should do?
So I said that the charge on each one would remain the same. So before we disconnected it, the 3-strap capacitor was at 20 volts and 60 coulombs, and the 6-strap capacitor was at 10 volts and 60 coulombs.
All right, so let me relay what you just said to the folks at home because I can't hear that. So what Matt said is he figured out how much charge was on each of the capacitors, probably by using Q equals CV or some arrangement of this. We knew what the voltage was before. So probably what you did is you went down to the one here in the bottom to figure out the total charge first. And that's where you got that it was 60 coulombs. And then applied that to each of these. Is that what you did? And then went one step further and used that to figure out that this was 10 volts and this was 20 volts. I'm just repeating for you guys at home what he said. So what did you do next?
So now that they're disconnected, they will have the same amount of charge, so 60 coulombs on each. So the 6-strap capacitor will still remain at 10 volts. Potential difference.
All right, so he's saying this one's going to be unchanged. Good. And
when you change the capacitance to the top one by multiplying by 3, you're then to find the voltage, you do the charge over the capacitance to do the voltage. So I got 20 divided by 3 is the voltage.
all right, so he used Q equals CV for the top capacitor, knowing that the capacitance increased by 3, charge didn't change. He said the voltage had to be divided by 3. Fine, that's exactly right. 60 equals 9V, so V is going to be about 7 volts, right? 6.6 repeating. So we went from having 30 volts to having 17 volts. Now, to figure out still whether it takes work to put the dielectric in there or not, we only have to look at this one capacitor because nothing changed about the bottom capacitor. So if we look at this one capacitor, we can say, well, 1/2 CV squared and apply that to the top capacitor. But I would rather us think about it this way. There's other ways to calculate the energy in a capacitor, which includes Q squared over 2C. I don't have to calculate anything to know the answer. If I just think of this for just this one opportunity here, just like we used 1/2 CV squared for the other one, Q didn't change, C increased. Energy storage went down. Right? C is in the denominator, so if C gets bigger, the total energy stored gets smaller. Which means that this is going to pull the dielectric out of my hand because the energy is dropping. Now, this is because the charges are there. They're not going anywhere. So as I go to move the dielectric in there, there's a force of attraction on the dielectric to pull it into the field because it's going to enhance the field, build it up greater. And it's also going to create a lower energy state. Almost all of nature attempts to get to a lower energy state. So because the energy goes down, the dielectric will be pulled from your hand. It's going to do work on the outer environment. Now, just so you understand, this is not a good way to apply force. We would never have a system like this where we try to push a dielectric out or pull a dielectric in. That's not a great way of like making a button, or you try to think of how could you use this force in nature. Think of things that you guys have used that are electronic switches. I want you to think about that for a moment, because how about automatic door locks in your car? You push a button and the lock pops up or pops down. That's converting electrical energy into physical work. We are talking directly about that right here. But this is not the way to do it. Even though it sounds like it is, With the capacitor, there's a lot of reasons why this would be the absolute worst way to try and create physical work from electrical energy. One of them is you have to have an exposed capacitor. And the amount of force we're talking about here is not very much. So we don't actually move things around using electric fields like this. There are much better ways to move things around. Not to mention the fact that in order to move this around, you have to have the dielectric already, halfway inserted. You'll just be pushing it out a little bit more or pulling it in a little bit more. But it's not effective because of what you have to do to the rest of the circuit. Look, at every single time we've done this, we've had a static circuit. And we've attempted to move the dielectric. What we're going to learn about later in the year is finding a way to move, I'll say the word dielectric, but it's a different word. Move our dielectric by changing our circuit. That's what we want. We had static circuits, right? The circuit wasn't changing while we attempted to move the dielectric in and out. What we would prefer is to be able to turn a circuit on and it moves out, maybe turn a circuit off and it comes back in. That's what we would prefer, something that we have a little bit more direct control over. That's going to require magnetic fields, and we'll get to those next semester. All right, so very thorough. How are we doing there, Alex?
The only question I had,
I know you had one. I told you guys last night he was going to have questions.
if you wanted to calculate the work to put the dielectric in on the first part, are you just subtracting
Wait, first part of what?
the first part, not when they're actually,
Yeah, I would track 1620 from the 900.
even though if you separate the capacitors, when you subtract them, you get a different number?
What do you mean?
Well, when you do 1/2 CV squared on the capacitor that you stick the dielectric in, it has 648 joules, while the original capacitor has 600 joules. So obviously it's not the same difference.
You can't compare what you're saying, separate the capacitors and then try and put the dielectric in. That's a different problem. The fact that our dielectrics are connected in the first, what he's asking is why is it a different answer if you separate all of the capacitors and try and calculate how much work is done? It's a separate answer because both capacitors are affected by the entrance of the dielectric into the system while the voltage is applied. Because while the voltage is applied, it changes the net capacitance of the system, which determines how much charge you are causing to flow into or out of the battery. And therefore, the work has to take into account the fact that you are affecting the bottom capacitor since it is connected to your potential difference. If you separate them, and then I'm assuming you separated them and then reconnected them to the power supply individually, you're only affecting the one capacitor, not the other capacitor. Remember, this picture right here, where we're looking at the two separate systems, that is two capacitors, but we're only looking at the equivalent capacitance for those moments. But they are connected to a voltage supply. So if I was to separate out just the 3 farad capacitor and compare it to what happens when it becomes a 9 farad capacitor, that is a different problem. The amount of charges affected by that are different than the amount of charges affected by going from that 2 farad to that 3.6 farad. I would bet it takes more work here because there's a bigger change in capacitance, right, when it's by itself. So that's why. Effectively, what we have to look at is how much charge are you having to bring out of the battery to deal with what you're doing to the system. When we had the other capacitor there, it's like we had a well of charges that we could use because the total capacitance was not affected as much by the insertion of the dielectric because the other capacitor padded it. Does that make sense? Sense at home? Moving on. So what do you think I should put in front of you next? What would make the most sense right now? Yes, sir. Well, yeah, I love that idea. But if I was to want to make sure I was being thorough before, hitting you upside the head with say a test tomorrow, what should you need to see now? Yes, sir.
If you wouldn't mind, Gauss's law and how it would be used in a capacitor.
Oh, That's not where I was going with this, but I'd be happy to. Then let me just throw out there then, since that's the suggestion, I would encourage you to consider redoing what we just talked about for a system in which we didn't have capacitors in series, but had capacitors in parallel. Although this problem, where I take and insert the dielectric into one of these capacitors while not disconnecting it from the power supply, is not terribly hard. The one where I charge the system and separate it from the power supply and insert the dielectric, that one's pretty tough. But you didn't ask to see it, so that seems like fair game tomorrow, because you guys feel pretty comfortable. And I like that. So I can talk about Gauss's law instead. Well, no, Max and Shreyas, they're experts here. They did it yesterday. They'd be happy to explain it to you, Max. How about you, Alex? Just check and make sure we're okay.
I mean, it would be nice to do that problem, but both would be good.
I do think we should see this. I'm afraid that you guys probably will have difficulty. I don't think you have difficulty with this part. And to prove that, I'm going to ask for you guys to show me your answer to this. Let's just do one thing here. Let's make this 90 volts. Dielectric still 3. So what I want to know, straightforward, what is the change in energy when I put the dielectric into the most effective capacitor? Which one's the most effective capacitor? It is, yes. That would be the most effective capacitor. So I'll give you, no, it can't be the end of class. Oh, fine. That's because we had a 30-minute homeroom for something that took 5. Well, that was a lot of fun for you. Guys, practice this tonight. I will post the answer, but I want you to do this. Listen close, because if you don't, then tomorrow when I ask you to perform it for 10 points and you get all mad at me, just remember this moment when I say you should try this both with the power supply connected and with the power supply disconnected. It's the power supply disconnected when you insert the dielectric that's tough, not this problem. So bye-bye. Have a nice day.